this problem goes, calculate the energy in joules per photon. And of the light that is emitted or absorbed in the following electron transition in the hydrogen atom. And so we talked, let's see. So in our picture of a hydrogen atom, the nucleus is of course in the center, and then surrounding that and I've sort of run out of space for my circles there, but we said that the n equals 1 energy level was the one closest to the nucleus, then n equals 2, n equals 3. Now this problem does a transition from n equals 3 to n equals 5. So I'm going to make more circles down here for 4 and 5. And we said a number of things about the Bohr model of an atom and the model of an atom in general. And that is, first off, these numbers for the energy levels go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and on to infinity according to the quantum mechanical model of the atom. So, but we're only interested in n equals 3 to n equals 5. And a couple other things we said about this model even before we do the calculation. And we'll talk about the equation in a minute. Let's talk about whether it's emitted or absorbed. So the electron in this case starts and n equals 3, and then ends in n equals 5. And what we said was that the starting point was the initial point, and the end point was the final point. Okay. And that the electron is getting farther from the nucleus. And let's just say the electron is moving away from the nucleus. Electron's moving away from the nucleus. And when it does that, it moves to a higher energy state. So lower energy is going to be closer to the nucleus, higher energy n equals 5 is a higher energy state. And so in order for the electron to move away from the nucleus and go to a higher energy state, it must absorb energy. So first off, this is going to be energy that is absorbed. And when energy is absorbed, energy is positive. And we can think of this as an endothermic process, and we will. So all of those things go together, and those are entirely consistent from when we were talking about thermochemistry in the previous chapter. Any questions about the picture that I've got right now? I haven't solved the problem, I know, but I just want to make sure we have a firm theoretical basis as to what's happening when we do this calculation. What's happening with the atom? Okay. Okay, well then let's actually do the calculation then. So this equation, again, on your conversion and equation sheet, it's going to be the one right here. Energy equals, and I'll go ahead and write this out, minus 2.18 times 10 to the minus 18. And then units of joules, those are going to be the units for the energy that we're solving for here. Then z squared, and 1 over, well, the conversion and equation sheet has 2's and 1's here. But in my lecture outlines, I used n final and n initial. And that's going to be 1 over n final squared minus 1 over n initial squared. Like so. So that's the adaptation we're going to use to solve this problem. And we talked about why that was in the lecture outline. Now, Okay, so a couple terms here we haven't talked about, although we did in the lecture outline, but just to be sure, Z is the atomic number. Atomic number, which is the number of protons. And this is a relatively straightforward question, but how many protons does a hydrogen atom have? Can anybody help me out?
1.
1, thank you. So Z is going to be 1 for hydrogen, and 1 squared is just 1. Thank you, Daryl, too, and Selden. So 1 squared is just 1. That term is going to drop out. And again, we talked about how this equation was developed for hydrogen first, and then they added the Z squared to make it more general. Now let's see, we've got our N final, which is going to be 5. We've got our N initial, which is going to be 3. Let's go ahead and plug all the terms in. So minus 2.18, move up a little bit, times 10 to the minus 18 joules. I'm going to leave out the 1 squared term because we've already done the math on that. 1 over 5 squared minus 1 over 3 squared. Okay. Now on my calculator, I'm gonna do 5, and then I don't know if you can see it, but I've got 1 over x button there if I hit my shift button. So I'm gonna do 5 shift 1 over x, and then I'll hit my squared button there. I don't know if you can see it there, that's a squared button. Minus 3 1 over x squared to get that term, and that term is going to be negative, which is good because I've got another negative over here, and I told you that my answer was supposed to be positive for this, and it will be. So now I've got this term. Now I can multiply it times my 2.18 times 2.18 exponent 18 minus, I forgot to put in my minus sign, so it's going to come out negative, but I know that my answer has to be positive. And my answer here, well, let's see here. So I've got 1.55 times 10 to the minus 19 joules. And that does not appear to be any of my choices. So let me go back and work on this one. I think I did everything correctly. Does everything look okay there?
Professor?
Yes.
I just solved mine and the assignment simultaneously as you solved yours, using the same method and everything, and it was correct. I think your answer choices are wrong.
I think, yes. Thank you, Daryl. Yeah, so I will go back and look at the different multiple choice answers here. I apologize for that. As you know, I designed all these questions over the summer, and we have discovered a couple errors here, so I apologize for that. I will take a look at that. And so let's wait on doing this until at least later this afternoon, for this is the 4th problem on the homework. Anyway, any questions about the approach to solving it? Oop, I can't quite fit everything on there. So I just left it in joules, but it says my answer is in joules per photon, as you can see there. So we can add, as we talked about, per photon to this. And I think that's just to make sure we don't use kilojoules per mole, the other set of units for energies this chapter. I will take a look at that.